And so hello, welcome back guys. So we're going to continue discussing Nikuradse's paper to see whether this K over here, or which is the epsilon which we see in our Moody chart, hopefully it is the same as the epsilon we see in our Moody chart, but it looks as if it is the same as this HS over here. This HS over here in this paper, conference paper, it is the same as this K which I'm highlighting over here. Okay, so these both of these correspond to some average roughness height. So yeah, we are just continuing the discussion from the last video because it took a bit long. We are talking about boundary layers and the height of the viscous boundary layer in relation to the roughness height, and that's what's causing all these different regimes to come about. We were also talking about what this log was. This was actually a log to the base of 10. That's why, according to this this paper, we have a HS of 3.5 here. 3.5 is actually 10 to the power of 0.55. So we just remove this logarithm here to make it easier for us. Okay, so we have the so this first regime is the effect for the effect of a smooth. I think the very thinness of boundary layers. All right. Okay. So, or rather, where the relative height or the dimensionless roughness height, or the log of that is very low, that we will have this expression over here, and it's corresponding to this expression over here where we see the 5.5. Next expression, we should expect the 6.59 from HS plus equals 3.5 to 7, or in this regime over here, we see 6.59 pop up here. And then we'll have a third regime from the logarithm 0.85 all the way up to 1.15, or this one will be 10 point something. We have A equals to, or the constant equals to 9.58. This is from 7 to 14, 9.58. Next one, this number 3, which corresponds to the number 4 over there. We will have 1.15, the logarithm, to 1.83. So A equals to 11.5 minus 1.62 logarithm of this log base 10 of this. So of course you change the base, then the coefficient in front is going to change. So you'll have 11.5 here, 11.5 here, and that's equals. Then you have a minus 0.7 here because this is a natural logarithm. And of course the last one, the last regime is HS plus more than 68, or K, the dimensionless coefficient, more than 6.68. You have B equals to 8.48. This is corresponding to this regime here, equation 21E. A equals 8.48. So if you want to just be a little extra cautious, you can do a 10 to the power of 1.83. So, okay, you do a 10 to the power of 1.83 just to see whether the numbers actually match. So this is 67.6. Okay, so 67.6, 10 to the power of 1.83, 67.6. And this is corresponding to 68 here. So all in all, it checks out very nicely. Just that this one has become converted into natural logarithm units, which I guess we are more comfortable with today, and it leaves no ambiguity because it uses this ln rather than a big log. Okay, so that's how we get that. So this k here, at least we can verify that this k here, it is the same as this hs, or rather this hs over here, and this HS plus is actually talking about the non-dimensionalized version. We're using friction viscosity and kinematic friction velocity and kinematic viscosity to normalize it. So that's good news. Okay, so question is whether this k over here, is it the same as this k over here in this relative roughness? Okay, so if they are the same, that means we can use this absolute roughness coefficient k here to substitute into our wall function right here, this hs plus, or this hs. We can substitute that into hs over here, and that will give us the relevant b function. Otherwise, yeah, we don't need to use these functions. We can the compressed version, it is given by this delta u equals 1 over kappa ln of 1 plus hs plus over exponential 3.25 kappa. So kappa equals to 0.41. Okay, so this delta u plus is stated here, very easy for us to use. Okay, so how are we going to verify that? So if you look earlier, okay, we scroll up through the paper, we will find something very useful for us. Okay, so yes, this expression here. Okay, remember we are talking about the third range. The third range is the thickness, is where the thickness of the boundary layer has become so small that all projections extend through it. Meaning to say, this is the third regime where the surface roughness is much bigger than the viscous sublayer, or thicker than the viscous sublayer. Okay, oopsie. Alright, so we can use this one. This is where this Moody friction factor, or this Darcy friction factor chart, has become flat. See, when you increase the Reynolds number, this friction factor doesn't really change much. So what is lambda over here? It is this friction factor, coefficient of friction, lambda over here. Okay, so based on that, we can sort of do a simple comparison. Alright, over here we have, at very fixed values of relative roughness, we can just simply read off the coefficient of friction, see, 0.06, for roughly a relative roughness of 0.03. Do note that this is K over the hydraulic diameter, which is of course for a circular pipe the diameter. However, that is equals to 2R. Whereas over here we see a use of R over K. So we'll kind of need to change that up a bit. So I'll just type it out in Word. Okay, so anyway, in my Microsoft Word, this is basically what I was looking into. Okay, so this is the three regime thing I was talking about earlier, and just so you know, v star is friction velocity. It's the same thing, the same nomenclature is used for different things. So this was the 5 equations we were talking about. And this is just to make sure that, you know what this log is, just to ensure that this log is actually a log of base 10. So I did an experiment there, and I just did a quick calculation and found out it is really base 10. So, okay. So the idea here is to compare this lambda to the flat part of the Moody friction chart. So in the Moody diagram, we use epsilon over hydraulic mean diameter. Okay, or it is also the same as divide var epsilon divided by 2R. Okay, so yeah, over here instead we have a lambda here. Okay, so this is actually half of, let's make this lambda expression in terms of relative roughness first. So first, I'm just going to copy and paste that. Okay, to the power of 2. I'm going to type in 1.74 plus 2 log base 10 of R by K. Okay, so I want this R by K in terms of relative roughness, E over D, right? So R by K, that is equals to K by 2R. Okay, so I'm just taking this surface roughness thingy here. Okay, and this is I'll just put on the right here, this one equals to the relative roughness. Okay, so why is that important? Because it makes it easy to compare. This relative roughness is what you see on the right over here, and that's what we want to use to compare, just very quickly. Okay, so the relative roughness equals to K over 2R. So we can write here relative roughness equals to K over 2R. Otherwise, equals to half K over R. So what can we know? K over R equals to 2 epsilon over dH. So it's 2 times the relative roughness. 2 times relative roughness. Okay? Alright, so very simply, we're just going to try to change this into some form of K over R. But we notice that this is R over K, so we just need to swap it around. We'll just do a negative sign out here, and then I'll just put R over K, or K over R instead. Okay, so and then I'll just substitute this K over R equals to 2 times the surface roughness. Okay, I'm going to put that here, and just to avoid confusion, I'll just put a bracket as well. Okay, so relative roughness is here. Okay, so now we have this, we can actually do into our Excel. Okay, I'll do a oopsie, surface roughness calc, surface rough. Okay, now I'll put a relative roughness here, relative. Ooh, I'm lagging. Okay, roughness. Alright, I have a relative roughness there, and what I have is then a friction factor. In the Moody chart, okay, so what friction factor is this? This is the Darcy friction factor. Darcy, Moody, friction factor. And then I'll have a Darcy, Moody, friction factor in the using the equation. So equation is this thing over here. Okay. Alright, so remember this thing has to be the flat part. Right? The flat part. So that's the easiest part to read. Okay, which part of the line has the flat part for us? So we can take a look at the relative roughness of 0.02, 0.04, so on and so forth, or 0.002. Okay, so let's put 0.02, 0.04, okay, 0.006, 0.008, 0.01, 0.015, 0.01, 0.15, 2, 3, 4, 5. Okay, 0.02, 0.03, and then I'll just drag down to 4 and 5. There you go. And we can just do a rough reading first. This one is about, let's say 2.6. Okay, I'm not going to give exact numbers, just a rough guesstimate. This one is closer to 0. Yeah, the coefficient is over here, 0.026. 0.026. Next one here is 0.029. Let's just give a rough guesstimate. I'm not going to be very accurate with it. 0.006, that is about 0.0032, I think. 0.03032. Okay. Next one, it's about 0.0036 or 0.036. 0.01 is closer to 0.038. This is a very rough one. Next one is 0.044 because this is a logarithmic, so I'm giving that about that much, 0.044. Okay, this one is almost 0.05, so I'll just read it there. This one is 0.0059, I believe, or 0.059. 0.04 over here it's 0.65 roughly, and this one is about 0.0715, give or take. Okay, so yeah, so I mean, if this epsilon here is equals to the k here, I mean, if this k here, it is the same as this k over here, then you know the numbers should match if I use this lambda equation over here. So let's try. So the equation is 1 over the square of, okay, so it's equals to 1 divided by, or I can just put to the power of minus 2. I can just put something to the power of minus 2. So 1.74 minus 2 times log 10. Now bracket, something else inside. 2 times the relative roughness. 2 times the relative roughness, which is here. Okay, so it's pretty close, and I can just drag it down all the way. You can see that the readings are pretty close. Alright. Okay, so I'll just copy and paste the evidence to show that, you know, it's really the same. So, oh wow, yeah, it's pretty close. Yeah, the readings are really, really close. So that's really nice to know. Okay. So, based on the readings, oh, this is really satisfying. Based on the readings, the K in the Darcy friction factor plot, which is this one, and of course this one, okay, K in this Darcy friction factor plot is the same as the epsilon, and is the same as HS. This is the height of the sand in this paper. Okay, not this one. Where is that paper? This one. In this paper. Okay, and both are the same in here. They're the same in Nikuradse. Let me check the spelling. Nikuradse's paper. Okay, so basically, yeah, basically when we have this expression here, HS plus, we can just use the law. I mean, we can just use this roughness coefficient here, just the same as what you use for your Moody diagram. Plug and play into this equation here. Delta U plus equals to, okay, maybe let me type that out. Delta U plus equals to 1 divided by 0.41 times ln of 1 plus HS plus over exponential 3.25 times 0.41. Yeah. So as long as we have this, okay, we have this U plus function, we just substitute the HS plus using this K. HS plus equals to K equals to K divide or K times V or U star over the kinematic viscosity. Okay, so that was quite a mouthful. Okay, so yeah. Alright, and the other notation, the famous notation, is of course epsilon. So yeah. So this is how we deal with the law of the wall for surface roughness. So surface roughness, yeah, it does play an effect in the law of the wall, especially for this transition regime. You see this transition regime they're talking about here, where increasing Reynolds number will cause the effect of roughness to increase, and of course the what do you call that, in the fully rough region, increasing Reynolds number doesn't really matter. Then is the smooth pipe region, or I think more aptly named the delta viscous sublayer, is much, or it's more than the surface roughness height, HS, or maybe I use a var epsilon here, just so it's hopefully less confusing. Yeah, so there's a lot of notations being used, but more or less they mean the same thing. So this video has shown that. So hopefully this will show you, this tells you how to get our surface wall correlations, okay, especially in the log law region. Yeah, especially in the log law region, we can take into account of the surface roughness over here in the log law region. Of course, in the viscous sublayer, you don't really need to account for that because of the aforementioned thing. We discussed it before. Yeah, so it affects the log law region. So that means the Van Driest relation doesn't quite work for surface roughness, but at least we do have some correlation, and I hope this has been helpful to you in knowing how to apply surface roughness, at least in theory. Of course, in various CFD codes, there are different ways of doing this surface roughness modeling, and that itself is another topic for another day. But hopefully this helps you know what the wall functions are about and how they take into account the surface roughness. So thanks for watching. I'll see you guys again. Bye bye.